Today we talk about the steady-state error design via integral control. So we will discuss how to design system represented in state space for a steady-state error. So we'll utilize the form of the state equation from the system in the figure to develop a controller. As a result, we will able to construct a system with zero steady-state error and the necessary transient response for a step input. Inside the dash box is a previous design controller. A feedback path from the output has been added to form the error E, which is fed forward to the control plant via an integrator. The integrator increases the system type and reduces the previous finite error to zero. Xn has been added at the output of the leftmost integrator. The error is a derivative of this variable. Xn dot equals r minus cx. These are the state equation for the figure. X dot equals ax plus bu. X sub n dot equals negative cx plus r. Y equals cx. This equation can be expressed as augmented vectors and matrices. However, the integral state feedback control u is equal to negative kx plus ke x sub n equals negative ke x sub n. So substituting this value to this value and simplifying, we will obtain this value. So as a result, the system type has been increased and we can design k and k using the characteristic equation associated with this equation to produce a desired transient response. Recognize that we now have an additional pole to position. So the effect of any closed loop zeros in the final design on the transient response must also be considered. One possible assumption is that the closed loop zero will be the same as those of the open loop plant. This assumption, which of course must be checked, suggesting placing higher order poles at the closed loop zero location.
To understand things well, let's have an example. Consider the plant of equations shown. First, to find, design a controller without integral control to yield a 10% overshoot and a settling time of 0.5 seconds. Evaluate the steady state error for a unit step input. Second, to find, repeat the design of part A using integral control. Evaluate the steady state error for a unit step input. Let's start with A. Using the settling time and percent overshoot requirements, we discovered that the desired characteristic polynomial is s squared plus 16s plus 183.1. This will be our equation 1. The characteristic polynomial for the controlled plant with state variable feedback is because the plant is represented in phase variable form as shown. S squared plus the quantity of 5 plus k sub 2 times s plus the quantity of 3 plus k sub 1. This will be our equation 2. After equating the coefficients of equation 1 and 2, we come up with this one. The controlled plant with state variable feedback represented in phase variable method is shown. We can calculate the steady state error for a step input as shown. So our answer for A is 0.995. For letter B, using the equation we come up earlier in our concept, it is now used to represent the integral control plant as shown. We can now determine that the transfer function of the plant is g of s is equals to 1 or s squared plus 5s plus 3. Thus, the desired third-order closed-loop system characteristic polynomial is the quantity of s plus 100 times s squared plus 16s plus 183.1 equals s cubed plus 116s squared plus 1783.1s plus 18310. This will be our equation 3. We can now obtain the characteristic polynomial of the system. It is s cubed plus the quantity of 5 plus k sub 2 times s squared plus the quantity of 3 plus k sub 1 times s plus k sub e. This will be our equation 4. After matching the coefficients of equation 3 and 4, we can acquire the following values as shown below. K sub 1 equals to 1780.1, K sub 2 111, K sub E 18,310. By plugging these values, we get the following closed loop integral controlled system. To test our zero assumption, we now apply and find out that the closed loop transfer function is T of s equals to 18,310 over s cubed plus 116 s squared plus 107.83.1 s plus 18,310. We have the desired transient response because the transfer function matches our design. Let us now calculate the steady state error for a unit step input. We get, so this will be our final answer for letter B. Therefore, we can conclude that the system behaves like a type 1 system.
In the case study, antenna control, design of controller and observer, we come out with a simplified forward transfer function with k equals to 200 as shown. This is the conceptual state space configuration showing plant, observer, and controller. So the problem, using the simplified block diagram of the plant for the antenna azimuth position control system shown in the simplified forward transfer function, design a controller to yield a 10% overshoot and a settling time of 1 second. Place the third pole 10 times as far from the imaginary axis as the second order dominant pair. Assume that state variables of the plant are not accessible and design an observer to estimate the states. The desired transient response for the observer is a 10% overshoot and the natural frequency 10 times as great as the system response above. As in the case of the controller, place the third pole 10 times as far from the imaginary axis as the observer's dominant second pair. Solution. We first design the controller by finding the desired characteristic equation, a 10% overshoot and a settling time of 1 second yield with a damping ratio of 0.591 and a natural frequency of 6.77. Thus, the characteristic equation for the dominant poles is S squared plus 8S plus 45.8 equals to 0, where the dominant poles are located at negative 4 plus minus J 5.46. The third pole will be 10 times as far from the imaginary axis or at negative 40. Hence, the desired characteristic equation for the closed loop system is S squared plus 8S plus 45.8 multiplied to the quantity of S plus 40 is equals to S cubed plus 48S squared plus 365.8S plus 1832 equals to 0. This will be our equation 1. Next, we find the actual characteristic equation of the closed loop system. The first step is to model the closed loop system in state space and then find its characteristic equation. The transfer function of the plant is shown below. This is the signal flow graph for G sub S equals to 1325 over S times the quantity of S squared plus 101.71S plus 171. Using phase variables, this transfer function is converted to the signal flow graph
and the state equations are written as follows.
We will now proceed in evaluating the controllability of the system by using the controllability matrix C sub m, which is shown below. As we can see, that the determinant of the equation of C sub m is negative 1. Therefore, the system is controllable. The plant with state variable feedback for controller design is shown. Continuing with the design of the controller, we show the controller's configuration with the feedback from all state variables in figure. We can now find the characteristic, the system matrix A minus BK. Thus, the closed loop system's characteristic equation is this. This will be our equation 2. So, we will now compare the two equations. We will evaluate the key sub i's as follows. So, key sub 1 is equals to 1832, key sub 2 is equals to 194.8, and key sub 3 is equals to negative 53.71. Before we proceed designing the observer, we tested the system for observability using the A and C matrices from the equation. The determinant of O sub m is 1325 cubed, thus O sub m is of rank 3 and the system is observable.
We now proceed to design the observer. Since the order of the system is not high, we will design the observer directly without first converting the observer canonical form. First, we need to find ALC, A, and C from these equations, along with L are used in evaluating ALC as follows. Then the characteristic equation for the observer is now evaluated as this determinant. From the problem statement, the poles of the observer are to be placed to yield a 10% overshoot and a natural frequency 10 times that of the system's dominant pair of poles. Thus, the observer's dominant poles yield as S squared plus the product of 2 times 0.591 times 67.7S plus 67.7 squared, which is equal to S squared plus 80S plus 4583. The real part of the roots of the polynomial is negative 40. The third pole is placed then 10 times farther from the imaginary axis at negative 400. The composite characteristic equation for the observer is now S squared plus 80S plus 4583 multiplied by S plus 400, which resulted to S cubed plus 480S squared plus 36,580S plus 1,833,000 equated to 0. Matching these two equations, we can solve the observer gain, which is I1 is equal to 0.286, I2 which is equivalent to 1.57, and I3 which is 1494. This will now complete the design including the controller and the observer. And this is the complete representation of the case study we have discussed. Here is the controller and here is the observer. In the figure A, it shows the impulse response of the closed-loop system without any difference between the plant and its modeling as an observer. The understood and settling time approximately meet the requirements set forth in the problem statement of 10% and 1 second respectively. While in figure B, we see the response designed into the observer. An initial condition of 0.006 was given to ×1 in the plant to make the modeling of the plant and the observer different. Notice the observer's response follows the plant's response by the time 0.06 second is reached.